This video is going to introduce linear differential equations. Linear differential equations play a very central role in the theory of DEs. Of course, right now we're just going to focus on linear first order differential equations. And just like with algebra equations, where linear equations were central, y equals mx plus b is really basic, and that's the first thing you learn. Well, this isn't the first thing we're learning in this course, but pretty early in this course we're going to jump into linear first order differential equations. So let me explain to you what it is. It's any differential equation of the form dy dt equals a of t times y plus b of t. The a of t and the b of t can be any expression at all. It could get very complicated in theory, but those parts only can involve t. So we have an expression involving t times y plus an expression involving t. So really the linearity is referring to the y part. Really, this differential equation is linear in y. The t parts to this don't have to be linear in the sense that you're used to. I mean, these parts could have t squares and square roots of t and cosine of t and lots of nonlinear stuff there. But it's the y that's sort of appearing in a linear way. So just something times y plus something. It's just like mx plus b is linear in an algebra sense, linear in terms of x, a number times x plus another number. So an expression times y plus another expression. That's the idea. Okay. Now, right off the bat, we want to talk about some special cases. One special case is constant coefficient, a linear constant coefficient differential equation. That's where the a of t, which is basically like a coefficient to y, is just a number, just a constant, and in that case we wouldn't write parentheses t, we would just write a. Okay, so there we would have dy dt just equals a number, literally just a constant times y. Now the b part can still have t's in it, but yeah, the a would be a constant. That's called a constant coefficient differential equation. And the second very important subcategory of linear differential equations is called homogeneous. And that's when the b of t is not there. It's 0. So that would be dy dt equals a of t y, and that's it. Okay. All right, so let me organize this in a slightly better way for you. Let's make a little table. So the general differential equation, linear, is dy dt equals a of t y plus b of t. And that is not constant coefficient, and it is non-homogeneous. Okay. Constant coefficient, as we just said, but still non-homogeneous, would just mean that the a is a number, doesn't have a t involved. Okay. Now the homogeneous versions, I'm just going to rewrite them, but without the b of t. So dy dt equals a of t y, right? And then, I haven't mentioned this one yet, but sort of the intersection of the two, a linear differential equation that is both constant coefficient and homogeneous. That would simply be dy dt equals a y, just a number times y. Okay, now right off the bat, let me get this lower right block out of the way. We have already seen this, and it might have just snuck up on you, but this is the differential equation that I mentioned is the one you should just always automatically know without any thoughts. This is the unlimited growth population model is one application of it. Yeah, this is just a number. The derivative is proportional to the quantity itself, and the solution is c e to the at. The a here goes right there, and there's an arbitrary c in front. So that is the solution. That's the general solution. So that is already done. Okay. Now, Actually, let's talk about this upper right block, dy dt equals a of t y. Now that's not necessarily as simple as when a is just a number, but it is separable. We have t stuff times y stuff, and just when it's linear, the y stuff is particularly simple. It's just a y. So we can separate it, and if I can just do that down here, perhaps bring the y over, bring the dt over. Okay, anti-differentiate both sides. On the left, we get natural log of y. On the right, well, I can't do this antiderivative unless I know what a of t is, but whatever that antiderivative is. Now, of course, we're also going to put the plus c. Let me explicitly throw in the plus c right now, because I want to do something with it. Okay, so, and then we would exponentiate both sides. So e to that antiderivative, and then it would be times e to the c, but as we've seen many times, we can just call that c, and I'll move it up front. And then I can get rid of the absolute values and absorb a plus or minus into the c. So in the end, I get y equals c e to the antiderivative of a of t dt. So that's actually the general solution for that case. Okay. So the homogeneous case is completely solved. Well, I should be careful about saying that. It's solved assuming we can do this antiderivative. But if we can, then we have it. One fact that I want to point out, it's not going to help us this moment. It's not going to help us right now. We already have our solutions. But it's something I want to point out right now that will help us later when we're doing second order linear differential equations, or we're doing first order systems of differential equations that are linear. So linear is going to go a little bit further than what we're doing today. And there's something that's nice that I want to point out right now. And it's very clear. It's that both of these solutions are, their general solution are all c times something. So I'm going to write this down as and call it a linearity principle, because it does come from the fact that we're talking about a linear homogeneous differential equation. And it's, yeah, it says that basically our solution is of the form c times something. This is just supposed to be a cloud. Of course, the something also is kind of special. It's e to something. But I don't want to, that's not the part I want to point out. It's just this part that it's the fact that it's c times something. C times an expression. In other words, to put this another way, if you have one solution to this, to either of these guys, then you can always just multiply by a constant and that will still be a solution. So you have one solution. 2 times that is a solution. 10 times that is a solution. Negative pi times that is a solution. Now, it would change the initial condition that it matches, and only one of those might match a particular initial condition. But in terms of just the differential equation, yeah, you can just multiply by any constant and it's still a solution. That's usually not the case for most differential equations, but it's true for linear homogeneous. Let me be very clear about that. This is true for linear homogeneous differential equations. Okay, so I just wanted to point that out. All right. Now we look at the left-hand column, the non-homogeneous case. And actually, let me pause on that. Let me just